In this video, we're going to look at integrating with inverse trig functions. So we've got to refresh a little bit about inverse trig functions. And I would recommend that you consider writing this as du over sine inverse of u. So this is going to be 1 over the square root of 1 minus u squared, and then I like to do u prime, and I like to do that on all of them. The reason is that if I'm doing dx of the sine inverse of, say, x squared, then I got to remember when I do this derivative, it's going to be 1 over the square root of 1 minus x squared, the quantity squared, multiply, because of the chain rule, the derivative of x squared, which is 2x. So I would recommend, as you're sitting there, to consider writing this with the u here everywhere multiplied by u prime, all the way through all of those. Now, when we are looking at trig integrations, you will notice on the trig integrations up above when we did the derivatives, we didn't have this a shenanigation thing. We had 1 minus. Everywhere you see here, you have these a shenanigation. Well, you can totally do this without having this a shenanigation and remembering this, provided, of course, we have the idea of what derivatives are. And what I mean by that is, now I'm going to go right to b. I'm going to ignore a because a is straightforward. This is going to be the sine inverse of x evaluated from 0 to the square root of 3 over 2. Nothing exciting there. Let's take a look at b. Now, if you're like, I don't remember anything that has 9 minus x squared. Well, if you rewrite the square root of 9 minus x squared as, I'm dividing both the 9 and the x squared by 9, so I have 1 minus x squared divided by 9, and this whole thing is underneath the square root. And let me rewrite this. I'm so excited. So I like to rewrite this as dividing both the 9 and the x squared by 9. So I'm going to divide this by 9. I have 1 minus x squared over 9, which I can rewrite this as the square root of 9, and then I have the square root of 1 minus x over 3, the quantity squared. And then I have 3, the square root of 1 minus x over 3, the quantity squared. Then you can see why up here, when we have a squared minus u squared, why we end up with u over the absolute value of a. Now, this allows me to say, hey, let u equal x over 3. Now, this is why that we do the whole du thing. Because I know when I do the sine inverse du of the sine inverse of x over 3, then this is going to be 1 over the square root of 1 minus x over 3, the quantity squared, divided and then multiplied by the derivative of x over 3, which is 1/3. So, going back to this, and you're thinking, why don't I just memorize what I have up above as being the u over the absolute value of a? Sure, memorize that, but I don't give it to you on the test. So you've got to figure out a way for you to remember how to get there. This is one of the ways, is just to algebraically manipulate this around. And I'm not done with this problem. I just wanted to show you the processes that I was doing. So if I don't have that memorized, that this is going to be the sine inverse of x over the absolute value of 3, which is just going to give me 3 plus c, then I can just rewrite this as saying, hey, let's rewrite this as 1 over, and then I'm going to factor out the square root of 9, which is 3, the square root of the 1 minus x over 3 squared dx. Now this is just a nice little let u equal x over 3 du is equal to 1/3 dx. Now you can see why this 1/3 and this dx gets replaced with du, and this gets replaced with u, and so my integration then becomes 1 over the square root of 1 minus u squared du, which we know is just going to be the sine inverse of u plus c. Of course, we're not solving for u, so we are going to write this as the sine inverse of x over 3 and then plus c. So that's another way of doing it if you're not like, hey, I got to memorize this stuff. So we're going to take a look at c, and I have the square root integrating from the square root of 3 to 1 of 1 over 1 minus x squared. Now, the thing about this is, first of all, the square root of 3 is much larger than 1. Well, not really much larger, but it is larger than 1. So I can rewrite this as the negative from 1 to the square root of 3 of 1 over 1 minus x squared dx. I'm going to pull that negative back through, and so I have 1 over the square root of 3. I'm going to make this negative go into the denominator, and I'm going to write this as 1 over x squared minus 1 dx. Now, if I think about my derivatives of my exponentials, or not exponentials, my derivatives of the inverse trig functions, not one of them matches this. We're actually going to be able to solve this when we're doing partial fraction decomposition. So partial fraction decomposition. And so we're gonna approach this with partial fraction decomposition, and we can't actually do that here right now in the inverse trig functions. So we're just gonna say, hey, that's a really nice problem, but I'm not gonna do it. Now, if you're like, man, I cannot wait to find out what this partial fraction decomposition shenanigation is all about, I'm going to go ahead and give you the answer. It's going to be the natural log, or actually it's 1/2 the natural log of the absolute value of x minus 1 minus 1/2 the natural log of the absolute value of x plus 1 plus, and then not plus c. And then it's going to be evaluated from 1 to the square root of 3. And so we're actually going to talk about this later. So I'm going to let that one rest for right now. Let's take a look at D instead. Now, D has the form of what I would expect when I have the absolute value of x minus 1. I mean, the absolute value multiplied by the square root of x squared minus 1. In fact, we know that this, when we get done integrating this, will be the secant inverse of x, evaluated from 1 to the square root of 2. So I get my trig formula sheet out, and the secant inverse of the square root of 2, so the secant inverse of the square root of 2, minus the secant inverse of 1. Well, the secant inverse of the square root of 2, well, that happens when we're at pi over 4 minus, and when I have the secant inverse of 1, that because secant is the reciprocal of cosine, that happens when we are at 0. So my answer is pi over 4. Don't forget that we are in radians, not degrees. All right, so with E and G are one of those ones that I personally like to do some factoring, because I like to have this of the form of the absolute value of x, the square root of x squared minus 1 in the denominator. I'm actually going to factor out a 16, the square root of 16. So I'm going to write this as a dx over the absolute value of x, the square root of 16. Excuse me. So I'm dividing both the 4x squared and the 16 by 16. This becomes x over, let me see, 4, so x over 2, the quantity squared, minus 1. So then this equals the integration dx over the absolute value of x. That square root of 16 becomes 4, and then I have the square root of x over 2, the quantity squared, minus 1. Now, I'm going to write this 4. I'm going to write this 4 right here as 2 multiplied by 2. There's a reason why I'm going to do this. So I have the integration of dx. I have 2, the absolute value of x, multiplied by 2, multiplied by the square root of x over 2, the quantity squared, minus 1. Now I'm going to say, hey, let u equal x over 2. That means du is 1/2 dx. So this 1/2 and this dx gets replaced with du. This x squared over 2 gets replaced with u. Now, 2u is equal to x. So the absolute value of x must be the absolute value of 2u. Now that has nothing to do with this 2. That 2 is still there. So then this becomes 1/2. That 2 right here is this 1/2 right here. The integration of 1 over the absolute value of 2u, because that's where I made replacement for x. And then I have the square root of u squared minus 1. Now, this 2 is still 2, whether it's the absolute value or not the absolute value, so I can bring that out front. So I have the 1/4, the integration of 1 over the absolute, and then don't forget the du, the absolute value of u, the square root of u squared minus 1 du. Now, we know that this then becomes the secant. So it is 1/4 the secant inverse of u, the absolute value of u, plus c. So this is equal to 1/4 the secant inverse of the absolute value of, well, u again was x over 2, so x over 2, and then plus c. And that is my final answer. Now, let's take a look at D. D is, or F, excuse me, F is really nice, straightforward. This is just the tangent inverse. The tangent inverse of x evaluated from the 1 over the square root of 3 to the square root of 3. The upper bound, so I have the tangent inverse of the square root of 3 minus the tangent inverse of 1 over the square root of 3. Looking on my trig formula sheet, this happens when we're at pi over 3 minus pi over 6, and whatever that is my final answer. So with G, what I'm going to do is I'm going to divide everything by 25. So I'm going to divide this by 25. I'm going to divide this by 25. I'm going to divide this by 25. And so I'm going to rewrite this as 1 over 25, the integration of dx over 1 plus 16 over 25x squared. Now I'm just going to rewrite this as 1 over 25, the integration of 1 of dx over 1 plus 4 over 5x, the quantity squared. So I know this is, again, the tangent inverse, so it is 1 over 25, the tangent inverse of 4/5 x plus c. Now, you're probably thinking, what did this 1 over 25 come from? So right here, this is dx divided by 25, which is the same thing as 1 over 25 multiplied by dx. So in other words, this 1 over 25 came out front of the integration. Now with h, we're going to do a bit of u substitution. So we're going to say let u equal. Now you're going to say, I want let u equal the square root part. No, we're going to let u equal the sine inverse of t. Then du is going to be 1 over the square root of 1 minus t squared dt. So this portion gets replaced with du. This gets replaced with u. So this is really the integration of 1 over u du, which we know is the natural log. So this becomes the natural log of the absolute value of u plus c. So this becomes the natural log of the absolute value of the sine inverse of t plus c. And that's it. Taking a look at I, this is going to be similar, and what I'm going to use for my u, I'm going to let u equal the numerator this time. So the tangent inverse of 2t. du is going to be equal to 1 over 1 plus 2t, the quantity squared, multiplied by the derivative of 2t, which is 2 dt. I am missing up here, I'm missing the 2, so I know that 1/2 du is going to get replaced with 1 over 1 plus 4t squared dt. So this gets replaced with 1/2 du. And so this then is equal to the integration of 1/2 u du. So this integrates into 1 over 4 u squared plus c. So 1 over 4 the tangent inverse of 2t plus c. Okay, so pretty much this is real similar over and over again. So like this one, we're going to let u equal the secant inverse of t squared. And you're thinking, wait a minute, when I take the derivative, how come this isn't an absolute value? Well, it's because t squared is going to be positive, so you don't have to do the absolute value. This one, you're going to let u equal the cosine inverse of e to the t. This one, you're going to let, this is going to be a 2 kind of u sub. First, we're going to say, hey, let u equal the tangent inverse of t. And du is going to be 1 over 1 plus t squared dt. Don't forget on this one, you do have to change your limits of integration. If you say let u equal the tangent inverse of t, that means when t is equal to 0, u is equal to 0. When t is equal to 1/2, u is going to be the tangent inverse of 1/2, and whatever that is not on the unit circle. So you would have to make sure you're out to so many decimals in radians. Now, m is the last one I wanted to look at. M is nothing like we've seen before. So what I'm going to do is I'm going to make it look something like we've seen before. So this is 75 over. If I take a look at m, I can factor out of the denominator, I can factor out a 25. Each one of these has a 25 in the denominator. Each one of those terms underneath the square root has a 25. So I'm going to factor out a 25, leaving me 3 minus 2 theta minus theta squared d theta. Okay. Now I know that this then becomes 75 over 5, and then the square root of 3 minus 2 theta minus theta squared d theta. And you're thinking, is this one of those ones that she's going to talk about later? And the answer is no. What we're going to do is we're going to focus in on the 3 minus 2 theta. 3 minus 2 theta. 3 minus 2 theta minus theta squared. I'm going to rewrite this as 3 minus, I'm going to pull out a -1, and then I'm going to have theta squared plus 2 theta. Now, what I'm going to do is complete the square. So I'm going to add whatever I need to do to complete the square, which is a 1. Now, if I were to multiply this -1 through, I'd get a negative theta squared plus 2 theta plus 1. But I pull that negative through, so it becomes a negative theta, negative 2 theta minus 1. That means to counteract that -1, I need to add 1. So what I have is 4 minus, and then I have theta plus 1, the quantity squared. So what this really is that I'm going to take 75, and I'm going to divide it by 5. And when I do that, I'm going to get the integration of 15 d theta. Then in the denominator, I'm going to get the square root of 4 minus theta plus 1, the quantity squared. Now, this is so similar to what I've had before, except for I want to have it 1 minus. So I'm going to rewrite this as the integration of 15 d theta, the square root of, I'm going to factor out a 4, leaving me 1 minus, and then I have theta plus 1 divided by 2, the quantity squared. And that's because what I did was I said, hey, 4 minus theta plus 1, the quantity squared, over 4 is the same thing as 1 minus theta plus 1 divided by 2, the quantity squared. That's all I did. All right. So then this becomes the integration of 15 d theta. I have the square root of 4, which is 2, the square root of 1 minus, and then I have theta plus 1 divided by 2, the quantity squared. Let u equal theta plus 1 divided by 2. And du is going to be 1/2 d theta. So this 2 and this 15 are going to be replaced with du, and that the 2 and the d theta. The 15 is just going to be pulled out front, and so I have 1 over the square root of 1 minus u squared du, which gives me 15, the sine inverse of u plus c, which is 15, the sine inverse of theta plus 1 divided by 2 plus c. And that is my final answer, and that's it for this video.